So in the first section, 1.1, we just sort of got our feet wet with exploring or reminding ourselves about how to solve linear systems or how we solved linear systems in the past. And we transitioned into the idea of using a matrix. We just kind of toyed around with one and solved it. We didn't formalize anything though, and so this second section is more about formalizing how we actually solve a linear system inside a matrix. And so it involves some vocab first on this page. And, it's not the most exciting stuff, but this vocab is important because I'm going to use the words on this page almost every video would be my guess. And so you want to be able to know what I say when I say leading entry or when I say echelon form and things like that. So let's get started. So the leading entry in a matrix. So remember, we could think of this as a linear system. And what we learned in the class last time was we can take linear systems and put them into matrices, right? And so what this says is the leading entry in a row is the leftmost non-zero entry. So I'm going to go ahead and circle the leading entry in the first row, right? So first non-zero entry. When we go down to the second row, the first non-zero entry is over here at the right, right? So these are what we would call the leading entries. Now that's a relevant concept, especially for echelon form, which is the next definition here. Right, so the word echelon is actually a Latin word that means ladder or step. And so echelon form is what we ended up with in the last session, right? We tried to get like something that looked kind of like this matrix right here, right? With just one thing in the bottom row, maybe a couple things in the next row, and you can kind of see how this looks like a ladder that you can kind of climb up, right? With zeros being empty spaces. So anyway, the word echelon form, or row echelon form. A matrix is in row echelon form if it has these properties. So number one, all the non-zero rows are above the zero rows. The way I just think about that is all the zeros are at the bottom. So if there's a row of zeros, you put it down at the bottom. Each leading entry each leading entry of a row is in a column to the right of the one above it. So if we want a leading entry, we kind of go down and to the right. So like this is leading entry, down and to the right, leading entry, down and to the right, leading entry, right? So this satisfies number two. And moreover, in every column below a leading entry, it's zero. Okay, and so I refer to this as row echelon form. I abbreviate this thing all the time. I'll call it REF, row echelon form. We put a matrix in row echelon form to see whether or not it has a solution, to see if it's consistent, which is a word we learned last time. Reduced row echelon form takes it a step further. So a matrix is in reduced row echelon form if it's in echelon form, but also the leading entry in every non-zero row is 1, and that 1 is the only non-zero entry in the column. Okay, so that's called reduced row echelon form. So it's fully reduced is what we might say, and I'll abbreviate that RREF. Okay? And so let's take a look at these matrices at the bottom of the page here and decide what form they're in. So let's go ahead and circle leading entries. I'm going to circle that with blue. And so the leading entry in the first row is right there. If I go to the second row, the first non-zero is right there. If I go to the third row, the first non-zero is right there, right? And so those are the leading entries. And moreover, this matrix right here is in echelon form because, first of all, it doesn't have a row of zeros, so that's not an issue. Every leading entry is to the right of the one above it, right? So we go down and to the right to get to the next leading entry. That's the way to think about it. So leading entry in the top left, then you go down and right to get to the next one. And everything below those leading entries are 0, right? So here's the leading entry, everything below it is 0. Leading entry, everything is below it is 0. So this is in echelon form. Or row echelon form. Again, I usually just abbreviate it REF. Okay. And when we do a similar kind of analysis on this, the next matrix on the right, again, here's the leading entry, down and to the right, leading entry, down and to the right, leading entry. So we have leading entries satisfying the ladder thing we're looking for, right? Below each leading entry is also a 0. And, moreover, they're all a 1, right? So it satisfies property number 4. And those leading entries of the number 1 are the only non-zero in the column, right? So they're the only non-zeros in that column, which is not the case here, right? We had zeros below, but not necessarily above on those. And so this matrix is in reduced echelon form. And again, I abbreviate that RREF. And so again, you can kind of think about reduced echelon form as just taking it a step further as regular echelon form. In other words, we could take this echelon form, make each one of those entries 1 by just dividing by the right thing, right? And then we could eliminate the values above the leading entries, and we could then get it into reduced form. And what we'll see is, in just a second here, really, is we get it into reduced form, so the form on the left, to see if there's a solution, to see if it's consistent. And then if it is consistent, so we know there is a solution, we then take it into reduced form to actually solve the system. Okay. The next thing on the bottom of this page is just more vocab. It's not exactly related to this, but I had a little bit of space, so I wanted to just squeeze it in here since we're talking about some vocab. Excuse me. So the first thing, the theorem, this is related to this. The uniqueness of row echelon form. This just tells us that every single matrix is row equivalent to only one reduced row echelon form. In other words, RREF is unique. Okay, so echelon form isn't necessarily, but RREF is. So, if you're working with someone and you're both working on the same problem, you might get different reduced forms. They'll probably look similar, but they'll be slightly different potentially. But if you work it into fully reduced form, reduced row echelon form, you should get the same thing, right? That's what this theorem's saying. The other thing that this is telling us at the bottom of the page is just what a triangular matrix is. Okay, so a matrix is triangular if it's either upper triangular or lower triangular. Okay, what does that mean? Well, an upper triangular matrix is when everything below the diagonals are 0. So if we had a 2 by 2 matrix, that might look like this. Right, so the diagonal entries are the ones that go right down the middle. Right, that's the diagonal. And everything below the diagonal, which is just one number in this case, is 0. So that's upper triangular. Lower triangular, the same thing, just the opposite, right? So lower triangular in the same kind of form would look like this. Right, so again, here's the diagonal. Everything above the diagonal is 0. And then there's actually a third term, which we might as well define here. A diagonal matrix is upper and lower triangular, which means it only has non-zeros on the diagonal. So the only non-zero entries are on the diagonal. So a 2 by 2 version of that would look like this. Something like that, right? So again, the diagonals are the only ones that are not 0. Okay, it's just a little vocab. It doesn't come up too much, but there are a few times where I say things like, oh, this is upper triangular or diagonal, and you just want to know what that means, right? Okay, great. So this is your chance to see if what I just said and we just learned about makes sense. So here's a couple hypothetical matrices. Okay, there's zeros in some of them for sure. Right, so there's 0 entries. And then we have, so let's just read it. So this says, are the following matrices REF? So are they reduced at all? And then we want to change the boxes or the stars to make it RREF. Okay? And so this is your chance to sort of pause the video and just sort of think about it. I'm going to run through them in just a second here. But you want to think about, do they satisfy these conditions? Okay, and I'll just go ahead and give you a hint that yes, they do satisfy 1, 2, and 3. But what would make them satisfy 4 and 5 is what you need to think about, right? Right, what would you need to change those stars or those boxes to Right, those could be any number, the stars or the boxes. What do you need to change them to make it fully reduced? Okay, so first of all, it's in row echelon form because it satisfies those three things, right? So there's no 0 rows, right? We look at this. Oh, this one. No, oh yeah, this one does have 0 rows, right? So this one has 0 rows. They're down at the bottom. This one doesn't have any 0 rows. Each leading entry is to the right of the one above it, and it's the only one in that column, right? So let's look at the leading entry. Leading entry, down and to the right. Leading entry, down. Oh, there aren't any more, right? And those are the only thing. Everything below it is 0. So that one satisfies REF, and the same thing's true with the other one, right? Leading entry, down right, leading entry, down right, leading entry, down right, right? So these are both in REF, just regular row echelon form. This is a yes, because the leading entries are to the right of the one above it. And there's zeros below each one. And so again, take a second, and what would you need to change the boxes or the stars to make them fully reduce? So again, in order to fully reduce it, we need to have those leading entries be 1, and we need to have that 1 be the only thing in the column. Okay, so again, this is your chance to pause it, or maybe you would just pause it for a second and think it through. I'm going to start running through them, okay? And so I guess the thing I forgot to sort of note here is each one, we're assuming each one of these boxes is not 0. That's what makes them leading entries. So each one of those boxes is a leading entry. And we're assuming they're not 0. I should have clarified that. Because if some of them are 0, then we might not be in row echelon form. So we're assuming those are non-zero. But what we need to do to take it a step further? Well, we need those leading entries to be 1, right? So these two boxes would need to be the number 1, because that's the fourth condition. And it needs to be only non-zero in the row, and so this star above that box needs to be a 0, right? So these things could be anything. We don't need to alter those at all. We just need to change those two things, and then that first star, right? So it would end up looking like this. Oops, that should just be a star. That could be anything there. Doesn't matter what's right here. Doesn't matter there either. Doesn't matter, doesn't matter. Right, so here's what we changed. We made this a 1, we made this a 1, and then we made that a 0. Right, so these things are the new things. Right, so the leading entries need to be the number 1, and they need to be the only non-zero in that column, and so that's what we just did there. And so this would put it in fully reduced RREF, reduced row echelon form. And so we would need to do the same thing with the next one, right? So we need this one to be a 1, we need that to be a 1, we need all the boxes to be the number 1, and that needs to be the only thing in each one of those columns. So we need to make this a 0, those would need to be zeros, right? Those need to be zeros, those need to be zeros. And so it would be the same thing that we just did, just a little bit of a bigger scale. So the first column does not change. This one needs to be a 1. Right, so that's new. It doesn't matter what this one is, but this needs to be, oh, that doesn't matter here. I thought there was a box. This one needs to be a 1, doesn't matter what, oh, no, that one needs to be a 0, of course, because it needs to be the only non-zero in the column. Pen is breaking on me here. So these two things are new. And this is also new. Just circling the things that have changed. We're now in this column. This needs to be 1. Those need to be 0. That needs to be 1. Those need to be 0. So it'll be like this. So all of these have changed. These two columns with the stars could be anything, right? There's no pivots in either of those columns, so those don't need to be 0, and they're not pivots themselves, so they don't need to be the number 1. So those stars can all just stay the same. Except I'm doing it in the wrong color. That needs to be 1. Those need to be zeros. These can be anything because there's no pivots in that column. Right, so this is all changed. Oops. Those should be zeros, of course. Right, this is, keep messing this up, but this is a pivot, and so that means these need to be zeros. So that's the pivot we just changed, so those need to be zeros, not stars, of course. And then the last column can be anything, because there's no, like I said before, there's no pivots in that column. And so they don't need to be the number 1, and they don't need to be zeros. So this would be RREF. Right? And in both these matrices, and all 4 of these matrices really, the stars could be any number, even 0. Okay, so we're just trying to, again, this is really important, and there probably won't be a day go by that we don't think about reducing something, and there's not going to be a homework that we don't think about reducing. So this is like the sort of the linchpin in a lot of this material. We think about row echelon form to look for solutions, and then we solve them using reduced row echelon form. That's what we're going to see in this section and many others. Okay, let's keep going here. So notice something about pivots. So let's just read this paragraph. Notice that if a matrix is in echelon form, okay, so think about this one on the left here, row operations are not going to change the position of the leading entries, right? In other words, if you're going from echelon form to reduced row echelon form, the leading entry remains in the same position. This leads to this definition. If a pivot position in matrix A corresponds to leading 1 in reduced row echelon form, then the pivot column is a column that contains a pivot position. So this is just sort of leading us down the road towards row reduction, right? So a pivot in a matrix A is in a location in A that corresponds to a 1 in the reduced form. And then we just say that that column is therefore a pivot column. In other words, if we looked at these earlier examples, column 1 is a pivot column and column 2 is a pivot column, because these are the 2 columns that have pivots. 3 and 4 are not. Right? Column 1, column 4, column 5, column 6, and what is that? Column 7, 8, 9 are pivot columns because they have pivots. All right, so let's go ahead and practice what we just sort of learned about a little bit. We're going to try to get this matrix in reduced row echelon form, right? It's one thing to sort of say we understand what it looks like, but how do we actually get something into reduced row echelon form? Well, it all starts with the top left-hand corner. And I guess maybe before we do that, let's just remind ourselves that this matrix is a system, right? So it's kind of like we have the x1 column, the x2 column, the x3 column, the x4 column, and then this would be the equal sign, right? And then we have the constants over on the right. So this is 3 equations with 4 unknowns, right? If we want to put something in echelon form, whether it's fully reduced or just regular row echelon form, what we want to do is start with the top left-hand corner, right? Just look at the ones we just looked at, right? The sort of the pivot that sticks the farthest out to the left is always in the top. So we want to kind of, when we're looking at a new matrix, we want to start as far up to the left as we can get and try to put a pivot up in that location. In other words, let's try to make this upper left-hand location, this is currently a 0, we want to make it into a pivot. And how are we going to do that? We're going to use the row operations that we learned about last class. So let me just pull those out real quick just to remind you of the 3 things we're allowed to do. We are allowed to multiply an equation by a non-zero. We are allowed to change rows, so just switch them. Or we can multiply a row by a constant and then add it to another row. All right, so we're going to do these 3 things to try to get this into echelon form. And so if we want to put a 1 up in that corner, the easiest thing to do would just be to take the 1 right here and get it up there, right? So we can switch rows 1 and row 2, because we're allowed to switch rows, right? And put a pivot up into the right. And so that's the first thing we're going to do, is we're going to switch row 1 and row 2 to get a pivot, in other words, the number 1, into the top left. All right, now remind you how we notate this. We write down the row we're changing, and then we write how we're changing it. And so in this case, since we're just switching rows, it's okay just to write switch rows 1 and 2 or something like that. But we'll see as we go through this, I'm going to be very careful about how we notate this stuff. Okay, so the first thing I'm going to do, this is equivalent to, we write it's not really an equal sign, we write like is equivalent to. And we're going to switch row 1 and row 2. And so that just becomes the following. Okay. So we got the pivot in the upper left. I'm going to box it in. Let's not mess that up. It's a pivot. We want it there. Great. Now, if we're gunning for echelon form, right, we want every leading entry, we want all the entries in a column below a leading entry to be 0. So we just put a leading entry that we want in the upper left-hand column, and we want zeros below it. Well, we have 1 0, but we want to make this a 0. And it's nice that those things are opposites, because if we just add that 1 to that one, it'll make it a 0. Right? And so I'm going to try to write this one out in detail so you can look back at it later. But the idea is you want a 0 below the pivot in row 1. And so what you're going to do is you're going to add, not R1, you're going to add row 1 to row 3. Right? Because it'll cancel that one out and make it a 0. And so the way we notate it, and let me just make this clear too, I'm going to box in the pivots. My box is a pivot entry. And we don't want to mess that up, so we box it in so we sort of know that it stays there. Anyway, the way we notate this is I'm going to change row 3, and how am I changing it? I'm going to add to it row 1. Right? That's the notation I'm looking for. If you did the R1 plus R3, that's telling me you're changing R1. Right? So you write down R3 first. Okay, so rows 1 and 2 don't change, so let me just rewrite those down. But then row 3 gets row 1 added to it, so this becomes a 0. We have 0 plus 1 is 1, minus 2 plus 1 is minus 1, 0 plus minus 3 is minus 3, minus 1 plus minus 1 is minus 2. Okay. So the first column looks good, right? We've still got our pivot here. 0's below it. First column is quote-unquote done. We don't need to mess around with that anymore. It's got a pivot, and it's got 0's below it. The next thing we want to do is we want to be able to go down and to the right and have a pivot. And so if that's currently the case here, right? We can go down to the right, and this would be the next pivot, but then we can't go down to the right again for the last row. Right? In other words, it'd be nice if this pivot was up here. And so next, let's try to get a pivot here. Right, so we want to go down to the right of that one. And so take a second to think how we're going to do that. How are we going to get a 1 right here? Well, we can just switch rows again, right? We can switch rows 3 and 2 to get a 1 into that location. Row 2 and row 3. All right, so we switch rows 2 and row 3, and it looks like this. And that's good, right? We've got a pivot here, down to the right, pivot here, and below that is a 0, so that checks out, and then down to the right, boom. So this actually satisfies REF. This is now in row echelon form. Okay, let me just review what those 3 things that we're looking for again. Leading entries, all non-zeros are not at the bottom. We don't have a net issue here. Leading entry of a row is you go down and to the right to get to the next one, right? And that should be the only non-zero. And that's exactly what we have. Leading entry, down right, leading entry, down right. The only things in those columns are the leading entry, the only non-zeros. Okay. So now that it's in REF, and let me remind you that the equal sign is right here, right? And so once it's in REF, we can actually tell that the matrix is consistent. And so I'm going to rewrite this on the next page, take it to the next page, and keep going from there. Just go ahead and put this back up at the top. Write it a little more nicer if I can. All right, let me just box in my pivots again. Pivot, pivot, pivot. So at this point, we can tell the matrix is consistent because we have it in REF, we have it in row echelon form, and we don't have that weird thing we got last time that says 0 equals not 0, right? If we look at the rows here, these don't say 0 x something equals not 0 on the right. And so at this point, we can tell the matrix has a solution, which is known as consistent. The system has a solution, I should say. We can tell the matrix is consistent, i.e. has a solution when we're in REF, because none of the rows says 0 equals not 0. And so we know this system has a solution, and so if we wanted to solve it, then we would want to fully reduce it. And to fully reduce it, we need to have those pivots be the number 1, which we already have, but then those need to be the only non-zeros in the column. Now the nice thing is, you can use this pivot, since it's a 1, to cancel that one out, right? Because this 0 is not going to mess this one up. So you put it in REF, you make them 1s in those spots, and then you use the 1s to cancel out everything in that column, right? And then once that's all canceled out, we'll use this one to cancel both those out, right? Because these zeros are not going to mess up the entries above it. So I'm just going to make a quick note about that, just to be clear about what we're trying to do here. So to get to fully reduced echelon form, we use each pivot to cancel the other non-pivots in each column. And it's kind of nice because a couple of them are 1s, but the third one will be our sort of first somewhat more advanced one, right? So the first thing I want to do is I want to use this one to cancel that one. So I'm going to do row 1 minus row 2. And that would look like this. Right, now the second column's all set. Got a pivot in the first one, it's the only non-zero. Pivot in the second, it's the only non-zero. And then we want to do the same thing with this one here. So first 2 columns all set. Then we want to use this value, this pivot right there, to cancel out the -3 above it. Now, what we can do sort of early on, you can think about multiplying this row by 3, right? So making that a 3 and that a 3, and then adding it to the row above it. So you can take it in 2 steps. If this is making sense, go ahead and do it in 1 step. Right? So you could just do right, so in other words, let me just bring those things up. You can do number 3. you can take one of the rows and add to it a multiple of another row. In other words, I'm going to take row 2, and I'm going to add to it 3 times row 3. Right? I'm going to make that into a 3 and then add it to there. It's going to also make that into a 3 and add it there. And that will get rid of the non-zero. Or the 0, I mean. The non-zero, excuse me. So the first row stays the same. Second row is going to change. We'll have 3 plus minus 3, that becomes 0. And then we'll have 3 plus minus 2 becomes 1. And then you don't have to actually leave the last row as being multiplied by 3. Like you multiplied by 3 and then added it to row 2, but then it's kind of like you multiplied by 1/3 and just made it back to normal. Right? And now it's fully reduced, right? We've got our pivots, pivot, pivot, pivot. So it's now fully reduced in our REF because it's reduced plus the leading entries are a 1 and there's zeros in the column with it. And just to kind of drive home the vocab, the pivot columns are the columns with a pivot in it, right? So the pivot columns would be this one, I'm running out of ink here. Grab another pen here. This one, and this one. These are the pivot columns. Again, pivot column just means it's a column that has a pivot in it. Now when we want to solve the matrix, so now that it's in REF, we can solve it. And so we write down the equations like we did last time, and now there's an REF, the last row is just going to tell us one of the answers, and then we can like plug it into the one above it to tell us the answer, etc., etc. Okay, let's write down the equations. We start by writing down the equations. Let me remind you that this is the x1 column, the x2 column, the x3 column, the x4 column, and then this is the constant, right? And this is the equal sign. So when we write down the equations, the first row says x1 plus 2x3 equals 1. The second row says x2 minus x3 equals 1. And then the third row says x4 equals 1. Oops, sorry, I didn't realize you couldn't see that. Right, so I literally just was writing each row down as an equation. And the third one just tells us one of the solutions, right? So the x4 is 1. So x4 is 1, that's part of the solution. Now what we're going to learn here is we can't actually get a solution for x3 on this one, right? There's no x3 in this equation to plug back in. So this is the kind of solution that has infinitely many possibilities. Remember the 3 types we saw in section 1.1 were one solution, no solution, or infinitely many solutions. And so this is the first time we're seeing infinitely many. So if we have what's called a free variable, which we will learn about in the next section, we solve for the pivots x1, x2. So let's get x1 and x2 by itself, and this ends up being the solution to this one. Right, x3 can be anything. It's what's called a free variable, and x4 is 1. All right, so when we write down x3 equals x3, that's how I would like to write down that x3 is what's called a free variable. You know, just in case anyone's sort of freaking out, like, oh, we haven't learned about a free variable. We're kind of learning as we go here, right? So we're solving systems without sort of fully defining it, and we're defining things as we go. By the end of sort of the next section, this should all be fairly clear, and you'll have some good practice with it. And that's the solution to this thing, right? So there's an expression for x1, there's an expression for x2, an expression for x3, an expression for x4. And so another way to write the solution, if we wanted to kind of write it in vector form, is x1, x2, x3, x4 equals what it says right there, right? x1 is minus 2x3 plus 1, x2 is x3 plus 1, x3 is whatever it wants to be because it's free, and x4 is always the number 1. Now we say x3 is a free variable because we can say that x3 is any real number. And that's why this one has infinitely many solutions. It has infinitely many solutions because you can plug any number into x3 and it will be something that satisfies this system. And so since you can plug infinitely many things in, that's what makes it infinitely many solutions. Okay. The final thing that I usually do in this class period is have folks work through this in-class activity in groups. We won't be doing this remotely in this online class here, but it is an opportunity for you to try some of the stuff. That's sort of the point here, right? And so there's 3 parts here, and in each one it's an exercise in row reduction. I would encourage you to try at least one of them. Just sort of pause the video and give them a go. I'm going to go through them, and so you don't necessarily have to. But, and usually what I actually do in class, I guess I'll write down the answers. Oftentimes I have students sort of write their answers up on the board, and then we just kind of look through them. But maybe it's more beneficial if I actually write down the answers specifically. And so I know there's a lot of words on this page, but what we're doing is we've got this system. Let's look at the questions 1 and 2. We've got this system and this system. In this system, we're going to write it in an augmented matrix. We're going to use the above rules. So these are the rules we're allowed to do, right? These are the things where the actions or what's the word I'm looking for? The operations we're allowed to do on a matrix. So we're going to put this into a system, use row reduction techniques to try to put it into row echelon form. And what we're going to do is we're going to see, once it's in row echelon form, we're going to see that it's inconsistent. So you should be able to see something that says 0 equals not 0. In the second one, we're going to do the same thing. We're going to put this into a system, and we're going to put it into row echelon form. But at that point, we're going to see that it's consistent. And so we won't get a 0 equals not 0 situation. I would strongly encourage you to try at least one of those just to get your feet wet with row reduction. And then you can watch me do it and see, if you went wrong, you can see where you should have kept going, or you can catch mistakes. Or if you got it right, you should feel good about it, honestly. And then the last question. This is a very common homework type question. I put questions like these on tests and things. It says, determine the values of h that result in each one of these things being consistent. Okay? Hint, reduce it. And so these are just 2 by 2s. And so reducing these systems, if we put these things in row echelon form, it just looks like this. Right? In other words, just putting a 0 like right there puts it in echelon form. And so it's really just like one step that you need to do, and then you need to think about what h makes 0 equal not 0 happen. Right? So we're kind of playing with row reduction. We're thinking about what it means to be consistent, etc. Again, I would strongly suggest you pause the video and at least try 1 or 2 of these. In class, I usually try groups of students try at least assign 2 of them, like question 1 and 1 of question 3, and then they write them on the board and we go through them together. I would strongly suggest you do that. At this point, though, I'm just going to go over them. So let's see here. Okay, I'm just going to do in blank sheets of paper. I don't think I put paper in here for it. Nope, you need a blank sheet of paper for this one. So problem 1, if we put problem 1 into a matrix, into an augmented matrix, that system I mean, it would look like this. This is definitely something that you should be able to do. I know you haven't done it a bunch by this point, but this is something that you should understand from the first section for sure. Okay. We want to pivot in the upper left-hand corner, just like we did in the last problem. And then what we're going to do is we're going to use that to eliminate the things below it, right? And so we're going to use the pivot to clear column 1. Right? In other words, multiply this by 3 and use it to cancel that one out. Multiply it by -4 and use it to cancel that one out. I'm going to do that in one step here, but you can do it in multiple steps. So in other words, I'm going to take row 2 and I'm going to add to it -3 times row 1. Right? Make this into a -3, use it to cancel that. In the same time, I'm going to take row 3 and I'm going to add to it 4 times row 1. Right? So make that a 4 and then use it to cancel that one out. So we're going to do that in one step here, and that's going to make both these zeros, and we're going to get column 1 squared away. Right? So the first row is not going to change. Right? This becomes a 4. It comes with, let's do the first one first. It comes a -3. You add it there. It becomes a 0. -3 times -3 is 9. If you add -7 plus 9, you're going to get 2. If you do 4 times -3, you'll get -12. 7 minus 12 is -5. Right? 4 times -3 is 12. If you do 12 minus 8, you'll get 4. So that's what happens to the second row. Do the same thing with the third one. This becomes a 4. Add it there, you get a 0. Multiply this one times 4, you get -12. -12 plus 6, -6. Multiply this one by by 4, and you get 16. 16 minus 1 is 15. Multiply this one by 4, you get -16. -16 plus 7 is -9. And so now the first row is all squared away. The first column is all squared away, right? We've got a pivot in the upper left-hand corner, nothing else below it. And we basically just do that for the other columns too. And there's more than one way to approach these. So if you did pause the video and you tried it and you're thinking about something different, or maybe you did something different, that's okay. At the end, we should get the same fully reduced form if we wanted to fully reduce it, right? Okay, let's go ahead and so we want this to be our next pivot, right? This is our sort of next pivot spot, so we want to go down and right to this one. And so let's go ahead and use it to cancel out the 6, and then we'll turn it into the number 1. In other words, let's do it in 2 steps. Let's do 3 times row 2. So that's not going to change, but the second row is going to change. And I was sort of thinking about doing that because I know I wanted to get this is going to be my next pivot, and it'd just be easier to cancel this one out while I have it as a -6, right? So just add this one to that, and then divide this row by 6 if we wanted to continue with it, right? So in other words, we could do row 3 at this point plus row 2 because those are going to cancel. And we would get this. Oh, that one cancels as well. And then over here we will have, oops, I forgot to change this to 12. And so this is also 12. Sorry about that. Right, when we multiplied the 4 times 3, it should have become a 12. And this is now row echelon form, right? Pivot, down to the right, pivot, down to the right, and that's kind of a pivot there, right? These are our leading entries. But we have an inconsistent matrix, and so you should think about why that's true. So we have an inconsistent matrix because the first row is okay, the second row is okay, but the third row says 0x1 plus 0x2 plus 0x3 equals 3. Right? So 0 equals 3. Huh? Right? So we got 0 equals not 0 in this last row. And so this is showing us that we have an inconsistent system. Which, again, remind you, means we have no solution. Right? When we were plotting 2D lines, it's like the lines don't intersect. And so this is, this is in 3D space now, and so it'd be like hyperplanes that actually don't all intersect in the same same spot. And so that's how we're thinking about that first one. We're just row reducing similar to what we just did. And seeing that we end up with an inconsistent matrix. All right, I'm going to keep going and do that with the second one. Okay. So in the second one, let me go ahead and write down the matrix again. And we've got a pivot in the upper left-hand corner already, so that's great. All right, so that's the system written in matrix form. That's our pivot in the upper left-hand corner. Now, we can make that into the number 2 and then use it to cancel that 2 out, right? In other words, we can take row 3 and add to it 2 times row 1. And when we do that, we're going to get column 1 squared away. Right? So the first 2 rows are not going to change, so I'm just going to rewrite them. First 2 rows are the same. But we multiplied the first row by 2 and then added it to the third row, and that becomes this. We'll have 2 plus 2 is 0. We'll have 0 plus 3, 0 plus 2. We'll have minus 4 plus 1 is minus 3. And we'll have minus 6 plus 5 is minus 1. And so again, column 1 squared away, right? We want to go down to the right. This is our next pivot. It's hard to use a 2 to cancel a 3, and so it might be helpful actually to divide this row by 2 first to make it into a 1, and then think about multiplying by 3. If you could also multiply by 3 halves, and that would also, or 1 half, excuse me. I'm sorry. You could also multiply it by 3 halves. Yeah, 3 halves if you wanted to make it into a 3. But if you don't want to mess around with fractions, you could just do something like this, right? You could just do like 1/2 times row 2. And just change row 2 into a 1 in the leading entry. And that'll help us cancel out the ones below it. Right, because we've got our pivot here. We've got our pivot here, that's what we want. Now we can make this into a 3 and cancel that one out, right? And actually after this step, I believe it becomes reduced. So we could do row 3 minus 3 times row 2, right? And so the first 2 rows, again, are not going to change, so I will just rewrite those rows. But then the third row is going to change. So we'll have 3 minus 3 is 0. We'll have 2 minus 3, which is minus 1. We'll have minus 3 minus 0. That doesn't change. And then we'll have 24 minus 1. Is that right? Times minus 3. Oh, I forgot to divide that one by 2. You've got to be real careful with this stuff. You can see how it's easy to make mistakes, right? So I was dividing each thing in this by 2 on this one, and I forgot to change this to a 4. Anyway, so then when you multiply this one by minus 3, it becomes 12, and then we'll do 12 minus 1, which is 11. Okay, so this is now in row echelon form. Not fully reduced, but we have a pivot, right, down to the right, another pivot, down to the right. I forgot to make that a 0. I think I said 0, but then I wrote 3 for some reason. Sorry about that. Down to the right, third pivot. All right, so we're all set there. And if we write out the equations, we don't get something that's weird, right? So the first line says x1 minus 2x4 equals minus 3. Right, the second line says x2 plus x3 equals minus 8. The third line says minus x3 minus 3x4 equals 11. And that's fine. Right, so this is consistent. We don't get 0 equals not 0. It's a consistent matrix. And so that means a solution exists. In other words, we don't get something that says 0 equals not 0. right? That's the thing we're trying to avoid. That's the thing that means inconsistent. We don't get that here, so there is a solution. Now, we're not finding the solution necessarily, right? The problem here is just get it reduced. Tell me if there is one. We'll worry about finding them in the next section. Okay, let's look at the final problem here, which I happen to really like these ones. You'll see them in the homework occasionally. Let's just remind ourselves what it says. So it's saying, like, figure out values that make these things consistent. And so what we want to do is we want to reduce it, which really just means putting a 0 down there. Right? If we have something that looks like that, that's in row echelon form. And then we'll think about what there's going to be an h over in this spot, maybe. And we'll think about what does that h need to be to make it consistent. That's the general idea. And these are actually quicker than you might think. They're usually just one-step kind of things, and then you think about it for just a quick moment. So number 3, the first matrix looks like this. Right? So we've got to pivot where we want it, right? We've got to pivot in the upper left-hand corner. That's fine. We just want to make the one below it a 0, right? So multiply this one by 3, subtract it from this one, and then we'll get it in row echelon form. In other words, take row 2 and subtract 3 times row 1. Right? And when you do that, the first row stays the same. The second row becomes a 0 here. This will become 3h, and then we'll do 6 minus 3h. Right? And then this will become minus 12, add 8, we get minus 4. Excuse me. This is now in row echelon form, so it's reduced. And we know it's going to be inconsistent if we see 0 equals not 0, right? So I'm going to do this in detail. Inconsistent, because people often get confused, but these are good problems. Inconsistent systems, have a row that says 0 equals not 0, right? And so, in other words, this is a 0 in that row. That would be a 0 if h is 2. So if h is 2 here, in other words, if 6 minus 3h is 0, we're going to get 0, 0 equals not 0. So if h is 2, the matrix becomes this. Right? And this becomes, the bottom row becomes the problem. This says 0 plus 0 equals negative 4. Right? And so h not equal to, as long as h is not 2, right? The only problem here is if h is 2, it makes that a 0. It'll make this part 0. So as long as h is not 2, we'll get a consistent system. In other words, has a solution. Right? So we just row reduced it, and then we're kind of thinking about what would h need to be right here to make this entry 0, right? Because then we'll get a 0, 0 equals not 0 situation. The second one's similar, but the outcome is different, right? So you're taking the same approach, but the outcome ends up being a little different. So here's what the second matrix looks like in number 3. Right? we have a pivot in the upper left-hand corner. That's great. Let's use that one to cancel out the 6 below it, and then we'll be in echelon form. So again, we're going to multiply this one by 3 and then add it to that one, right? So we're going to take row 2, add to it 3 times row 1. And when we do, the matrix looks like this. So 0 there, right? This becomes, we multiply by 3, so this becomes 9. 9 plus 9 is 18. And then this becomes 3h, so we'll have 5 plus 3h. This is fully reduced. So even if you didn't do this one yourself, if you didn't bravely pause it and try it yourself, stop right now and think about, right, the h is over on the other side of the equal sign. It's part of the constant side now. Is there something we could plug into h that would end up with 0 equals not 0? Well, the answer is no. Even if this ends up being 0, that's okay, because that just says 18x4 equals 0, right? So any value of 0 on the right-hand side is okay. Any value of h, excuse me, even if that makes it 0. What you want to avoid is 0 equals not 0, with 0 being on the left. So let me write that down in detail with some explanation here, in case this isn't clear. So all values of h work. Make this consistent. Since we can't ever obtain 0 equals not 0, right? In other words, even if you plug in h equals minus 5/3, so that's h equals minus 5/3 will make this term 0. Then what we get is 0 plus 18x2 equals 0. In other words, 18x2 equals 0. In other words, x2 equals 0. And that's okay. It's okay for x2 to be 0. What you want to avoid is adding a bunch of stuff up that's not 0 and getting 0. It's okay for the variable to be 0. It's just not okay to add up a bunch of zeros, like in this one, and get something that's not 0. So in the second one, any h works. And again, these are very common homework type, test type questions, because putting an h in there really forces a student or someone taking a test to think about what's going on and row reduce something by hand. And so I do include things with h's in them. You probably saw it as early as the first homework. All right, I'm going to stop here in the middle of this section 1.2 and finish it for the in the next video.